All right, getting into our second lesson here in topic 2 of Unit 1, looking at arithmetic and geometric sequences. Now we can define those and determine what type of sequence we are looking at. So first in this warm-up, just looking at some prior knowledge, recognizing patterns here. Write the next 3 terms of each sequence and explain how you generated them. So if we're looking at number 1, what's happening there is it looks like it's being multiplied by -2. If you think of that, the following pattern, that's why we have a negative and a positive, a negative and a positive. So like I'll just write the next term in each series for space. So if we wrote 16 times -2, the next term would be -32. Now for the second one, the pattern going on there is looks like we have a same difference each time going down by 7. So we're subtracting 7. So if we're looking at the next term, 32 minus 7, our next term would be 25. Okay, for the third one, we got 1, then 5, then 17, and then 53. A little tougher to figure out here because what's going on is 2 different operations going. It's being multiplied by 3 and then adding 2. These type are definitely the most difficult to figure out because there's multiple operations involved. So it's times 3 and then adding 2, not subtracting 2, then adding 2. So in other words, 1 times 3 is 3, plus 2 is 5. 5 times 3 is 15, plus 2 is 17. So we'd get a rather large number if we went one more row. 485 times 3 plus 2, and our next number in that series would be 1,457. And then the last one there, number 4, back to a little bit more simpler. All that's happening there is we're adding 6 to the previous term. 4 plus 6 is 10, 10 plus 6 is 16, and so on. So 22 plus 6, our next term would be 28. All right, so goals today is just being able to determine the next term in a sequence, recognizing and knowing what an arithmetic, and geometric sequence is, understanding terms common difference and common ratio that we'll get to, and being able to graph those, and recognizing that graphical behavior. All right, so moving down to our next page. Now I'm going to be just flipping down to them because it says cut out sequences A through P located at the end of this session. So if you scroll down to those, and I'm flipping to them as well. We'll scroll all the way down. There we go. So we're looking at these sequences when we're talking about these questions we're going to ask. All right, so first one says determine the unknown term of each sequence, then describe the pattern under each sequence. So again, I'm going to go back to that page and we're just going to work on that page determining the next term in the sequence. So if we look at, I'm on the wrong page, that's I. Need to start at A. There we go. All right, so starting at A, 45, 90, 180, 360. So what's happening there is multiplying by 2. Okay, if we just had the first 2 terms, you wouldn't know is that 45 times 2 or are we adding 45? But by having that third term, we can figure out that it is multiplying by 2. Okay, so the next terms in the series, I'm just going to write 2 again for space. If we did 360 times 2, we're at 720. And then at 1,440. Let me rewrite that where I'm not covering up that other number. So 1,440. Okay, if we go over to B, what's happening there is we are adding 2. -4 plus 2 is -2. -2 plus 2 is 0. So our next 2 would be 4 and then 6. For C, we are being multiplied by 3. So -2 times 3 is -6. -6 times 3 is -18, and so on. So for C, the next 2 in the series, if we did -54 times 3, we get -162. And if you do that times 3, we get negative 486. And for D, we got two different possibilities here, how you ever want to look at it. We have each term is going up by one more on the next one. So in other words, 2 to 5 is plus 3. 5 to 10 is plus 5. 10 to 17 is plus 7. So we could follow that pattern. So if we now went up 9 for the next one, 17 plus 9 would get us to 26. And then if we went up 11, our next one would be at 37. So there would be our next terms in the series. There's another way we could look at it also as the term number. Remember, term number is just counting the term in the sequence, squared plus 1. Okay, so what's happening there is saying term number mean like item in the series. So term number, the second one, that's the 5. That's term 2. So 2 squared. Oh, sorry. Looking at the wrong one. So we'd have term number, the series, that would be 3, actually. The first term number in the beginning would be 0 back here. So 5 is term number 3. 3 squared is 9 plus 1 is 10. There we go. I had it backwards as far as your term number there. All right, E. A little more difficult when we're dealing with fractions. To figure out what you're adding and subtracting by. The easiest thing, use a calculator. See what the difference is. Convert that decimal to a fraction like we were doing back at the beginning of the first unit to see that difference. And when you do that, you're going to find that 4 to 7/4 is going down 9/4. 7/4 to negative 1/2 is also going down minus 9/4. So if you were to continue following that pattern, the next term in the series you would get negative 5, and the next term in the series would get negative 29 over 4. Okay, again, take your calculator, subtract it. It's going to give you a decimal. Convert that back to a fraction. It's much easier to see what that difference is. You could leave it as a decimal if they were giving us decimals, but since we're working with fractions, we want to leave it in the same form. All right, for F, what's happening there is, you could say it two different ways. If you want to say multiplying or dividing. We're really dividing by 10, because it's moving the decimal a tens place to the left each time. Another way to look at it, since we're going to talk about mainly a ratio of multiplying more, is it's multiplying by 0.1. So for instance, the next term in that series, if we move the decimal one more to the left, would be 0.1234, and then the next one would be 0.01234, and so on as we move that decimal. Okay, for G, we're looking at that series for G. It is two operations going on again. We are adding 1, but the sign's changing, so then it's doing times negative 1. So in other words, the next one, 5, we add 1 to get 6, times negative 1 would be negative 6. Add 1 from 6 to 7 times negative 1, and now we're back to a positive number, positive 7. All right, and then H, negative 20, negative 16, negative 12, negative 8, negative 4. Pattern that's going on there is we're just adding 4. Much easier one to spot. If we add 4 again, we're going to get to 0 and then 4. Now, I'm going to leave the next page that has graphs I through P. You should try those on your own, see what we get, and see if we fit into the certain categories we're going to look at in the next step. So I'd take a minute, pause the video, try those on your own. All right, so we're going back to the questions that were asked about those sequences. Sort the sequences into groups, list the letters of each sequence, and provide a rationale. I think the easiest ones to spot is some are multiplying, some are adding, or multiplying or dividing, some are adding or subtracting. So two most obvious groups, and this is including the ones you should have done on your own, A, C, F, J, M, and P are all multiply or divide. And then B, E, H, K, and N are all adding or subtracting. Now, I didn't include ones that some of them had multiple operations where we were adding a number and then like the one we multiplied or added one and then multiplied by -1. Technically, we got two operations going on there. But I think those are the two most obvious groups. So what mathematical operations did you perform in order to determine the next term in the sequence? Okay, some were adding, subtracting, multiplying, or dividing. And some were doing the same every time. Let me fix that. My pen got a little off there. Every. Some are the same every time, and some required more than one operation. Like again, that example I gave you of the one where we added one and then multiplied by -1. All right, moving on to the next page, and we're going to define the two different types of sequences that we were just looking at. Okay, for some sequences, you can describe a pattern as adding a constant to each term to determine the next term. For other sequences, you can describe the pattern as multiplying. Okay, even if you think you're subtracting, we could refer to that as adding a negative number. So if we are adding a number each time, that is an arithmetic sequence. It's a number in which the difference between any two consecutive integers is a constant. Okay, in other words, the sequence of numbers in which a constant is added to a term to produce the next term. And we call it the common difference, which is kind of backwards to how you think about it. When we hear difference, we think subtract, but it's the difference that we are adding that number to get to the next term. So here's a great example of it. Consider the sequence shown, 11, 9, 7, 5. So it's going down by 2, so we could say we are adding -2. Okay, the question right below that, when you get to the next page, suppose a sequence has the same starting number as the sequence in the worked example, but the common difference is 4. How would the pattern change? So each term would add 4. Is the sequence still an arithmetic sequence? Yes. It's still a common difference. And is it possible to write the first 5 terms of that sequence? Yes. So going back, that first term up there was 11. So 11, add 4. I'm not going to write the add sign. Add 4, and we would get 15. Add 4, and we'd get 19. Add 4, we'd get 23. Add 4, we'd get 27. So there would be the first 5 terms with a common difference of 4. All right, so looking down at the next question, analyze those same sequences that we just went through earlier, including the ones you did on your own, that had the page with letter I starting. List the sequences that were arithmetic, so the ones that were adding or subtracting the same number every time. And those were B, E, H, K, and N. So again, if I just go back down to those, for instance, B, we were adding 2. E, we could say we were adding -9/4, even though we think of it as subtracting 9/4. Okay, another one, H. H was one of those we did. It was adding 4 each time. So we had a common difference on all of those. Okay, so just again, a couple of the common differences in those ones we saw. B, it was 2. E, it was -9/4. H, it was 4. We added 4. And then 2 from the page you should have done on your own, so you can check these right here. K, it was adding or subtracting, you could say, -1.5. So adding -1.5. And N was adding -20.5 or subtracting 20.5. All All right, so the other type of sequence. A geometric sequence. Okay, it's a sequence of numbers in which the ratio between the two consecutive numbers is a constant. So in other words, we are multiplying by the same number each time. Whatever number you're multiplying by is called the common ratio. So an example we're giving us here, 1, 2, 4, 8, we're being multiplied by 2 to get the next term. So 2 is the common ratio. So for question 3, how would the sequence that has the same starting number change in the work example if the common ratio was 3? You'd say each term, sorry, my pen keeps messing up, each term is multiplied by 3. Is the sequence still geometric? Yes. It's still a common ratio. And writing the first 5 terms in that sequence. So 1 is the first term, times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 will give you 81. So there would be our first 5 terms in that sequence. Okay, moving on to the next page. Suppose a sequence has the same starting number as the sequence in the worked example, but the common ratio is 1/3. Each term would multiply by 1/3. Another way you could think of that is dividing by 3 is what's happening. Okay, so is the sequence still geometric? Yes, it's still a common ratio. And write the first 6 terms. Okay, so starting with 1 was the first number we were dealing with. So if we do 1 divided by 3, our next term is 1/3. If you do 1/3 times 1/3 or divided by 3, you get 1/9. So really you're just multiplying that denominator by 3. So we'd have 1/27, 1/81, and if you went one more, 1/243. So that would be our first 6 terms. Okay, another example, very similar. Suppose the sequence has the same starting number as the sequence in the worked example, but the common ratio is -2. How would the pattern change? So each term would multiply by -2. So is the sequence still geometric? Again, yes. Still a common ratio. And if we were going to write those first 6 terms, again, we're starting at 1 times -2 would be -2. Times -2 would be +4. Times -2 would be -8. And times -2 would be +16. If we went one more for 6, 16 times -2 would give us -32. So there would be our first 6 terms with a common ratio of -2. All right. Number 6, consider this sequence shown, 270, 90, 30, 10. Devin says he can determine each term of the sequence by multiplying each term by 1/3, so the common ratio is 1/3. Chase says that he can determine each term of the sequence by dividing each term by 3, so the common ratio is 3. Who is correct? Well, they are both correct that both of those operations will give you the next term in the series, but only Devin is correct about what the common ratio is, because the common ratio is what you multiply by. So in other words, yes, we're dividing by 3, but that is multiplying by 1/3. Okay, so they're thinking about how to get the next term is both correct, but as far as defining what the common ratio is, the common ratio is what you multiply by. So we would just say Devin is correct. Now, would they both get the right answer as far as the next terms in that sequence? Yes. All right, moving down to the next one. It says, consider those sequences you cut out at the very beginning. So that last page again, list the sequences that are geometric. So again, if you were to go back through those, the ones that are geometric, A, and I'm going to go ahead and list the common ratio. Common ratio was 2 we multiplied by. C, common ratio was 3. F, common ratio was 0.1. That was the one I told you we were dividing by 10, but we need to know what we multiply by to have the common ratio. J, common ratio was 1/2. M, and these are some on the page you should have tried, that common ratio, -1/4. So it's really dividing by -4, but we have to know what that is as a multiple. And P, common ratio was -3. So just to go back and look at some of those, like A was 2, C was 3. So if I go back and pull some of those up, A, common ratio of 2, C, the common ratio we multiplied by 3 each time. Okay, 8, consider that the sequences that are neither arithmetic nor geometric. List these sequences and explain their consequences. So these are the ones that most of the time had 2 operations involved. Okay, the ones that had that were D, G, I, L, O. So those have no common difference or common ratio. I'd like to give an example. For instance, D was that one we said went up by 3, then up by 5, then up by 7, up by 9. There's no common difference there. It's going up by different amounts each time. All right, next page. Consider the first 2 terms of the sequence, 3 and 6. Dante says this is how I wrote the sequence for the given terms, 3, 6, 9, 12. Kira says this is the sequence I wrote, 3, 6, 12, 24. Who is correct? Well, both are correct. Because if we just have the first 2 terms, either one of them could be right. We could be doing times 2 to get 6, and then 6 times 2 is 12, which is what Kira has. Or if we're only given those first 2 terms of 3 and 6, it could be plus 3 each time, which is what Dante said. And go up 3, and then add 3 to get 9. 9 plus 3 is 12. So typically we most often need more than 2 terms to be able to figure out what sequence is going on there. So 10, using the terms given in question 9, write a sequence that is neither arithmetic nor geometric. It says then have your partner, so whoever you're sitting with, tell you what the pattern is in your sequence. Okay, you could come up with many different answers here. Just one, I'll write one example. I'm going to do 3, 6, 9, 15, 24. And my pattern I came up with there is adding the 2 previous terms to get the next one. So those had to be 9. 6 plus 9 adds to be 15, and so on. So that would be an example that doesn't fit either category, arithmetic or geometric. Okay, how many terms did your partner need before the pattern was recognized? Again, that's up to you and your partner you're working with on this for you to discuss. 12, consider the sequence 2, 2, 2, 2, 2. Identify the type of sequence. Okay, it could be both. If it's arithmetic, you could say it's adding 0. Common difference is 0. If it's geometric, I could say that it is multiplying times 1. And that would also work. So again, that sequence, even given unlimited terms, we could call it either or, arithmetic or geometric, and be able to be both of them correct. All right, next page. This is one that you probably try on your own with the graphs. It says, as you've already discovered when studying functions, graphs can help you see trends of a sequence, and at times can help you predict the next term in the sequence. So it says the graphs representing the arithmetic and geometric sequences from the previous activity are located at the end of this lesson. Cut out these graphs, match each graph to its appropriate sequence, and glue them on to the graph section. So this would be something on your own, removing these graphs, or you could just identify them as you go. So for instance, I'm just going to list a couple of them for you to see some examples as you go through and work through this on your own. So sequence A that we did should correspond to graph 1. Sequence B should correspond to graph 4. Let me give you 3 of them. C should correspond to graph 2. Okay, I want you to spend some time looking at those graphs and matching it to the one going on. So just to go look at some of those examples I wrote. A to graph 1. So A was multiplying by 2, so it should create some sort of exponential function, and it was starting at 45. So if I go to the graphs page, graph 1, exponential function increasing. Doesn't look exactly like it's starting at 45, but you got to keep in mind the scale of that graph. That's 3,000, so it's a very broad scale stretched out there. Give you another one we looked at. B went to graph 4. So sequence B was adding 2 each time. So that's going to create a linear graph, adding the same amount each time. Graph 4, there it is. There's that linear graph, adding 4 each time. Okay, so again, go through those graphs, see if you can match up which ones go with those sequences we are looking at. Again, if you're multiplying by a number, we're looking at an exponential function. If we're adding or subtracting the same number, we're looking at a linear function. So 2 and 3, it's most to discuss amongst yourself. A lot of options here. What strategies did you use to match the graphs to the corresponding sequences? You could say like what I was just mentioning. Common differences. So arithmetic. Produce linear graphs. Or you could say common ratios. Produce exponential graphs. So there would just be one example of a strategy you could use. Okay, 3, how can you use the graphs to verify that all sequences are functions? Again, if you're looking at a graph and we're determining if it's a function, you're using the vertical line test. All right, and then finishing up, I would advise you to pause the video, try to work through these on your own, and then I'm going to go ahead and answer them, and you can check how you did. So 1, the first term of a sequence is 8, and the common difference is 12. So if we're adding 12, we'd go 20, 32, 44, 56. For 2, first term of the sequence is -9. Common ratio, so now we're multiplying, is -2. So that would give you 18 times -2 is -36, times -2 is +72, and times -2 is -144. Okay, 3, the first term of the sequence is 0, and the common difference is -6. So we're adding -6. So you get -6, then -12, -18, -24. And then the last one, the first term of the sequence is -3, and the common ratio is -4. So we're multiplying by -4. So -1/4, I'm sorry. So -3 times -1/4 would give you +3/4, times -1/4 would give you -3/16, times -1/4 would be +3/64, and times -1/4 again would give you -3/256. So essentially, you're multiplying that denominator by 4, and then the 3 in the numerator, because we're multiplying by -1, is alternating between negative and positive. All right, that brings us to the end of this lesson. In the next lesson, we're going to look at recognizing the function that's creating the equation that's creating these sequences, so we can be able to match it to the sequences that we're identifying.